Welcome to the third video in the video series on motion. Now, at the end of the previous video, I assigned the following homework for you to attempt. And to refresh our memories, let's just go through it. The problem was that there's a motor vehicle traveling at a velocity of 30 meters per second, and then the brakes are applied and the vehicle is brought to rest in 6 seconds at a uniform deceleration. Sketch the velocity versus time graph, determine the acceleration using the graph, sketch the change in position versus time graph, and lastly sketch the acceleration versus time graph. So let's now look at the solution to these problems. Because the deceleration is uniform, we can assume that the velocity versus time graph is going to be a straight line. The initial velocity is 30 meters per second and the final velocity is 0 after 6 seconds. We obviously must label our axes appropriately. The vertical axis is the velocity axis, measured in units of meters per second. The horizontal axis is the time axis, and the units are seconds. And so starting at 30 meters per second and ending at 0 meters per second after 6 seconds, we get a straight line that descends like that. Now, from mathematics, we should know that if we have a backward sloping straight line like this, that the gradient should be negative. So the B question asks, using the graph, determine the acceleration of the motor vehicle. So the acceleration is the gradient, which is rise over run, and the rise is the change in velocity, the run is the change in time, because this is a velocity time graph. Using the mathematical formula for gradient, y2 minus y1 over x2 minus x1, making this point x1, y1 and this point x2, y2, we get that the gradient is going to be 0 minus 30 on the rise. In this case, it's not a rise, it's actually a fall. And the run is from 0 seconds to 6 seconds. And so minus 30 divided by 6 gives us negative 5 meters per second squared. Now, when we work with acceleration and with velocity, we must be very careful that we are aware of what the negative sign means. Now, in this particular case, the velocity is positive. The motor vehicle is moving in the easterly direction, and even though its velocity is decreasing, it is decreasing in a positive direction. So the motor vehicle has not changed direction, it has gradually slowed down in the easterly direction. So what does this minus sign mean? Well, the minus sign means that the acceleration is west. But wait a minute, this car is not accelerating, this car is decelerating. Precisely. If your acceleration is negative, but your velocity is positive, this implies that the net force, which acts in the same direction as the acceleration according to Newton's second law, that the net force is acting in the opposite direction to the actual motion of the vehicle. So while the velocity is always in the same direction as the motion of the object, that is not necessarily always true of the acceleration, because the acceleration is in the direction of the net force, and in this case the net force is a braking force which is acting against the motion of the vehicle, hence bringing the vehicle to a standstill. So getting a negative acceleration here with a positive velocity means that this object is decelerating, but in an easterly direction. The C question asks us to sketch or draw a position versus time graph, or a displacement versus time graph, or a change in position versus time graph. Now, from the previous example that we covered, in video number 2, we have learned that when you have a velocity versus time graph, that the area under a velocity time graph gives us the change in position of the object. Now, in order to generate a position versus time graph, we need several points in order to be able to plot it. So what I've done here is I have chosen these points on the velocity time graph in such a way that each point is at 1 second increments from the previous point. Now, using exactly the same method that we used previously, we are going to work out the area under the velocity time graph for each of these time intervals, but always starting at 0 seconds, because we want to plot the total change in position of the object with respect to where it originally was at 0 seconds. So I'm going to go through this very quickly. The first change in position calculation involves that area, which gives us 27,5 meters. We've used the area of a trapezium, which is the sum of the sides divided by 2 times by the base. In this case, the left-hand side, or the left-hand height of the trapezium, is 30 meters per second. The right-hand height is 25. Add them together, dividing by 2 gives us the average height of that area, times by the width, which is 1 second, and we get an area of 27,5 meters. Doing this now for the area under the graph there, which is over a 2 second interval, we get 50 meters, then 67,5, 80, 87,5. And my advice to you is to pause the video here and to check the solutions here with your solution that you did when doing the homework. So the last calculation involves calculating the total area under the velocity time graph for the 6 seconds. And if you look closely here, you'll see that the left-hand height is the original 30 meters per second, but the height on the right-hand side is in actual fact 0. So this is in actual fact the area of a triangle. We could have rewritten this as half the base, which is 6, times the height, which is 30, and we would have got 90 meters. So plotting all these data points into a table and then plotting them, and here too I would ask you to pause the video and check that you have each of these points correctly plotted on this graph. Now note that here too, this graph is not a straight line, but rather a parabola. And this is going to make more sense when we look at certain equations of motion later on in this video. But if you look carefully, you'll see that the change in position diminishes or reduces per second. And why is that? Well, is the vehicle not slowing down? Is it not slowing down by 5 meters per second every second? Yes, it is. And if that's the case, then the amount of distance or change in position per unit time is going to decrease over time. And that's exactly what we are seeing here. And that is why it is not a straight line, but rather a parabola. Lastly, we are asked to plot the acceleration versus time graph. And over the 6 seconds, the acceleration is minus 5 meters per second squared, which we represent with a straight line. Now, I remember when I started studying motion, the acceleration was always a difficult one for me to conceptualize. Even though the acceleration is constant, it doesn't mean that the motion is constant, because the acceleration is the change in the velocity per unit time. So it means that the velocity is changing per unit time at a constant. So it still means that the velocity is changing all the time, and hence the amount of distance or the amount of displacement or the amount of change in position per unit time is changing as well. In the previous video, we referred to the equations of motion, and to review, the equations of motion deal with the following quantities. If an object has an initial velocity which changes over time because of an acceleration or a deceleration to a final velocity over a particular time interval delta t, and the change in position is delta x, then we proved that the following equation is true, that v final equals v initial plus a delta t. And we derived that from the fact that the acceleration is in actual fact the gradient of the velocity versus time graph. We also derived another equation of motion, this one delta x equals v initial plus v final over 2 delta t. And we've just used this equation to work out the areas under the velocity versus time graph in order to get the change in position over a particular time interval. So now what we're going to do is we're going to move on to proving the third and the fourth equation of motion which we use in this topic on kinematics. So referring to equation A and B in the previous slide, if we take equation A, which says that v final equals v initial plus a delta t, and we substitute it into equation B, which says delta x equals v initial plus v final over 2 delta t, then we get the following equation, that vi plus vi is 2vi plus a delta t over 2 delta t, which is, keep this in the bracket. We then multiply delta t in using the law of distribution, so 2vi delta t is the first term, a delta t times delta t is a delta t squared, and this is all over 2. We now divide 2 into each of these terms in the numerator, and we get that delta x equals v initial delta t plus a half a delta t squared, and this we're going to call equation C. Once again, I want to draw your attention to the fact that this is not a normal equation. This is a vector equation. Certain of the quantities in this equation are vectors and hence are dependent on the direction. So delta x is the change in position. It is a vector quantity. V initial is a vector quantity, and the acceleration is a vector quantity. Delta t is not a vector quantity, it's a scalar, and therefore we leave the arrow off the delta t. If we now manipulate A in such a way that we make delta t the subject of this equation, then taking vi to the left hand side becomes minus vi, and then dividing by A on both sides, we get delta t equals v final minus v initial over A. We can call this modified form of equation A star. Now substituting A star into B, delta t is now replaced by v final minus v initial over A. When we multiply these two together, we get a difference of 2 squares. And when we multiply 2a across, we get v squared final minus v initial squared equals 2a delta x. Taking v initial squared to the other side, the sign changes, and we get v final squared equals v initial squared plus 2a delta x. Rewriting it with the arrows for the vector quantities, v final squared equals v initial squared plus 2a delta x. Now, I would like to bring to your attention that when we multiply vectors, things get a little bit complicated because there are different ways in which we can multiply vectors in mathematics. This particular way of multiplying vectors is called the scalar or the dot product, and it produces a non-vector quantity. So v final squared is in actual fact not a vector, even though you're multiplying a vector by a vector. V initial squared is also not a vector. And it's very important that we view A and delta x as vectors taking the signs which represent their directions into consideration, because when we multiply these two together, the sign that comes out is critically important. So if this is negative and this is positive, then a negative times a positive gives us a negative. So now we have the four equations of linear kinematics. Now I explicitly refer to linear kinematics because there's also a rotational kinematics where we study systems and objects that are moving in a circular manner. But these equations are not for that. These equations are for objects that are moving in a straight line. So the four equations here you get on your formula sheet in tests and exams. So you need not worry too much about learning them off by heart. But when you've used them enough times, then you find that, like any tool that you use enough times, it becomes part of you. And so you need not even look at the formula sheet anymore. But please note, these are vector equations, and so directions are important. So let's look at an example of how one could use these equations of motion to solve a kinematic problem. So a racing car has an initial velocity of 100 meters per second, and it covers a displacement of 725 meters in 10 seconds. Determine its acceleration. Now, this is quite a straightforward question because the motor car, or should I say the racing car, is actually traveling in one direction. We are going to give you problems where we are going to have to look and take into consideration the change in direction of an object in its motion. But for the time being, let's develop a technique that's going to help us with the more complex problems. So the first thing I would like to suggest is, as we did with forces, is to assign a sign convention. So I'm going to define the original direction of motion as positive and the opposite direction as negative. Now, the initial velocity is 100 meters per second. The initial velocity is there. And because velocity is a vector quantity, we do well to assign a positive or negative sign to it. So because it's traveling in the positive direction, I am explicitly going to put a plus sign in there. We do not know what the final velocity is going to be. We do not know what the acceleration is. And we're going to have to find that out. Now, the change in position is also a vector quantity, so I'm going to assign a positive sign there because the change in position is in the direction of motion, which we've assigned as positive. And now, while albeit that data lists are not mandatory, I would strongly suggest that when you do these problems, that you set up a data list so that you can clearly see what you have and what you don't have. And especially when we get to two-body problems, where we have to take into account the motion of two separate bodies moving simultaneously, then it's very useful to have two separate data lists for the two objects that are moving. So I'm going to now fill our data list, and we see here that the delta x, and I'm going to put a vector sign on top of it. Delta x is plus 725 meters. V initial is plus 100 meters per second. V final we do not know. The acceleration we do not know, and that is in actual fact what we are being asked. We're being asked to determine the acceleration, so we are looking for that. and delta t is 10 seconds, and that is not a vector quantity, so we need not worry about assigning a positive or a negative to it. So now we have the data list, and we can clearly see that we are missing the acceleration and the final velocity of the object at the end of the 10-second time interval of its motion. Now, the next thing we need to do is we need to determine which of the 4 equations we are going to use. So I've written down the 4 equations of motion that you would get off your formula sheet, and now we're going to do an analysis of what quantities we have and which ones we don't have. So we have delta x, and I'm going to tick wherever I see delta x. We have v initial, and so I tick wherever we have v initial. We don't have v final, so I'm going to put a little cross there and there. We don't have the acceleration, and that is in actual fact what we're looking for. So I'm going to put a little cross there, and we were explicitly asked for it. So I am going to put a little box with a cross wherever I find the acceleration. We do have the time, delta t, so I'm going to put a tick above delta t. And so you wouldn't do this all the time, but in the beginning it's good to do this to get a feel for which of the 4 equations you can use depending upon what quantities you have been given. Now, in algebra, for every unknown that we want to solve, we need an equation. And if you have an equation that's got 2 unknowns in it, you cannot solve it. You need another equation to help you to solve for the 2 unknowns. So looking in equation 1, one can see that there's in actual fact only one unknown, and it happens to be the one that we're looking for. So we can use this equation. If we look at equation number 2, and you can see I've left out the fact that we don't have v final there. You can see that equation number 2, we could use equation number 2 to work out v final because the rest of the unknowns are actually known. In equation number 3, we don't have v final and we don't have the acceleration, so you can't use that equation unless you have either v final or the acceleration. And equation number 4, we could use equation number 4 to find v final if we had the acceleration. So we're being asked to determine the acceleration, so we are going to use equation number 1. And so we need to rewrite it, as I'm going to do here. I'm going to write it as delta x equals v initial delta t plus a half a delta t squared. And in the NSC syllabus, it's not required that you put in the arrows as I do, but I do it so that I am aware of whether I'm working with a scalar or a vector quantity, and therefore I am conscious of signs when I'm working with vector quantities. So looking now, we substitute in delta x is plus 725, so I'm going to put that in, plus 725 meters. V initial is plus 100 meters per second. Delta t is 10 seconds plus a half times the acceleration, which we don't know. Delta t squared is 10 seconds squared. And so we can rewrite this as 725 equals 100 times 10 is 1,000 plus, if we look here, 10 squared is 100 times a half gives us 50, so this is plus 50 acceleration. And I'm now going to leave the arrow out. It may sound as if I'm being inconsistent, but it can be quite tedious to keep the arrow as long as you ensure for the time being that you put the arrow in the original equation, just so that you are sensitive to the fact that the sign, positive or negative sign, is really important for that particular quantity. So taking the 1000 across, we now have that 725 minus 1000 equals 50A. And that works out to minus 275 equals 50A. And now we want to solve for A, so we divide by 50 on both sides. What you do to the one side of an equation, you must do to the other side of an equation. That's a fundamental rule of algebra. And so if we divide by 50, we get that the acceleration here is in actual fact minus 5,5 meters per second squared. Now, we need to interpret this. Science and physics is not just about getting numerical answers. It's about solving problems, physical problems, getting solutions, and then interpreting what the physical meaning of that solution is. Now, if we look here, we can see that the velocity of the vehicle is positive because it's moving in the positive direction. The fact that the acceleration is negative should tell us that this car is in actual fact decelerating, like we found in the previous example when we worked with the graphs of motion. So this acceleration, the direction would be in the opposite direction to the motion, so we're going to write it as that. This is going to be 5,5 meters per second, and because we don't have east or west, we're going to write it as in the opposite direction to motion. And that means that the net force acting on this object is actually in the opposite direction, in the backward direction to the motion of the car. So more than likely, this car, the driver of this car, has applied brakes to slow the vehicle down. Now, it wasn't asked in this particular problem, but I would like you now to pause the video and attempt to work out what the final velocity would be for this vehicle when it has reached this point here, where it is 725 meters from its original position. Using V final equals V initial plus A delta t, and having V initial, having delta t, and having calculated the acceleration, we can now calculate V final because it's the only unknown in that equation. So substituting in for V initial plus 100 meters per second, remember our sensitivity to the sign, and even though it makes really no difference mathematically if you put the sign in, the fact that you put the plus sign in there shows that you have a sensitivity to the fact that this is in actual fact a vector quantity. Then adding the acceleration, which is minus 5,5 meters per second squared, timesing by the total time interval of 10 seconds, we can then work out that V final is 100, and note here, minus times plus, plus times minus times plus, gives us a minus, and 5.5 times 10 gives us 55. So V final is then plus 45 meters per second. Keep in mind that V final is a vector quantity. So this plus sign here is in actual fact a direction. So we're going to rewrite it fully as V final is 45 meters per second in the original direction of motion. Now, in the way that I teach kinematics, I want to encourage you to view the graphical and the mathematical representation of motion as being equal in importance. So don't view graphs as more important than the equations of motion and vice versa. And hence this is the reason why in this video series I choose to teach this section, teaching graphs and the equations of motion in parallel, so that you continually see that they are completely, intrinsically and implicitly related to each other. So what I would like to ask you to do now is to pause the video and to sketch the velocity time graph and to sketch the change in position versus time graph and to sketch the acceleration versus time graph for this particular object in this problem. And by sketch I mean that you don't have to draw a super accurate graph with a large amount of data points. When we refer to sketching in this section, we are referring to you being able to draw the basic shape of the graph with a few significant points like the intercepts of the axes and if there is a turning point. Now, in drawing these graphs of motion, I would like to suggest that when you draw these graphs, that you draw them one underneath the other. And the reason for this is that what it does is it helps to reinforce your idea or your concept of the relationships that exist between the quantities and the graphs as we go deeper into the study of motion. You'll see as we go along. So if we look at the velocity time graph, well, the data that we have is on the right hand side here. These quantities we calculated, we solved for them. These quantities we were given. So the initial velocity was 100 meters per second, and so I'm putting in 100 there, and we have a definite point there, data point there, and after 10 seconds the final velocity was 45 meters per second, which would be less than halfway between there and there. This is a sketch graph, so it's not to scale. We are just drawing some significant points and the basic shape of the graph. Now, this is uniform deceleration because of the fact that the acceleration is a constant and because it is negative. So we can be confident that the graph is going to be a straight line between these 2 points, which we are going to draw like this. And we know this because the gradient of a velocity time graph is the acceleration, and the acceleration is a negative constant, so this line has a negative gradient. This is the most difficult of the 3 graphs to draw, because this graph, as you will soon see, is a parabola and not a straight line as is this graph and this graph. So I'm going to choose the easy one first. I'm going to draw the acceleration versus time graph, and I'm going to draw it here, and I'm going to say, well, if this is -5.5, the unit is meters per second squared, then the graph is going to be a horizontal straight line, and it's going to remain minus 5.5 for the duration of the 10 seconds. Now, in the past two examples, we used areas under the velocity time graph to work out what the change in position graph was going to look like. Now, to be quite honest with you, very often we don't have the time to work out all those areas. So through practice, we learn that certain types of motion have certain shape graphs. Now, the fact that the velocity is decreasing means that every second the amount of displacement is going to get less. And so in the previous example, when there was a negative acceleration, we found that the graph was in actual fact a parabola that had a shape basically like this. Now, we know that the total displacement is 725 meters. So after 10 seconds, this value here would be 725 meters. Now, these graphs are related to the equations of motion, and I would like to refer to the following two equations of motion. So we learned that V final is V initial plus A delta t. Now, if we view V final as the velocity at a certain time point, and now I'm going to refer to functions in mathematics, if we view the velocity as a function of time, which it indeed is, then it is equal to a constant V initial, which is in actual fact this value here, which is the intercept of the vertical axis, which in mathematics we would refer to as c. And the acceleration is the gradient, which we would say is m. So if we looked at this, if we said here that change in v over change in t, that would be the gradient m, which equals the acceleration, times delta t, which is the independent variable, then we can actually write this in a form that is quite common, and you would have seen this in mathematics. We can write it as follows. We can write the v, in place of the v we can write y. And in place of the v initial we can write c. And in place of the a we can write m. And in place of the t we can write x. Because x is the independent variable on the horizontal axis, and y is the dependent variable on the vertical axis in mathematics. And so what we get here is the equation of a straight line in mathematics. I'm going to write it here. Y equals mx plus c. And so we can see that this straight line's equation in the y equals mx plus c form, or what they call the gradient intercept form, is in actual fact this equation of motion. Can we do the same for this curve? And the answer is yes. If we refer to the following equation, and that's going to be delta x equals v initial delta t plus a half a delta t squared, and we rewrite it as follows: x of t because x is indeed a function of time. As time moves along, so the change in position, the x value varies. And if we write the half a delta t squared term first, half a delta t squared, and then the v initial delta t, and then I write a 0 here. Then if I write this form here, y equals a x squared plus bx plus c, then you should recognize this as the general form for a parabola where the y-intercept is 0, and that's exactly what we find there. The y-intercept is 0. And the leading term is a half times the acceleration. Now, in mathematics, you should have learned that if your leading term is positive, then you have a parabola that smiles up, as it were. And if your leading term is negative, then it has a smiley down, like a negative curvature, in comparison to a positive curvature. Now, looking here, our acceleration is negative, which would mean that this leading term is negative, and therefore that's why we have a parabola that curves like that, as opposed to in the very first example in the previous video where we had positive acceleration and the position time graph curved up like that. Now, there's a lot of mathematics on the go here, and I don't want to confuse you, but I think it's critically important that what we teach you in physics, we relate to what you've been taught in mathematics, because that really is how deep learning takes place, is when we can make connections on a fundamental level between different topics and different concepts that are applied in different contexts. I would like to draw your attention to the fact that just as the velocity time graph's gradient gives us the acceleration, and as we can see here, this is a backward sloping straight line which has a negative gradient, and therefore the acceleration is a negative value. And notice it's constant because there's a constant gradient here. So too, the gradient of the position versus time graph gives us the velocity. And we'll delve more into this at a later stage, but if we look at the gradient of the position time graph as we move along, we find that albeit that it is positive, it's becoming less steep. And so here, the gradient of this graph is changing position over changing time, gives us the velocity. We can see it's got a high positive value, but as the graph starts to flatten out, the gradient becomes less positive. And this is critically important, especially when we start having to draw sketch graphs in more complex situations. But for the time now, that is enough mathematics, and I would like you now to practice on the following problems. So in this problem, which I'm giving you for homework, an object starts from rest. It moves in a straight line with a constant acceleration. There's the uniform acceleration again, and covers a distance of 64 meters in 4 seconds. So it's very similar to the example we've just done. It asks for the acceleration and the final velocity. So A and B are very similar to what we've just done. Then it asks at what time will the object have covered half the total distance? In other words, 32 meters. The answer might not quite be what you think it is initially. And at what distance will the object have covered half the total time, which would be 2 seconds. And then I would like you to sketch the velocity time, the position time, and the acceleration time graphs for this particular system. And lastly, I would like you to look at this problem where a ball is thrown downwards with a velocity of 10 meters per second. So that's the initial velocity when it leaves the person's hand, and the ball travels directly down, but it's now under the influence of gravity, and it travels from a balcony 15 meters above the ground, and we give you the gravitational acceleration. Now, I'm being a bit naughty here. I'm already going into a grade 12 topic, which is called vertical motion, where we look at the motion of objects under free fall, in other words, where they purely are under the influence of the force of gravity. But for the time being, you have enough physics in order to be able to do this, because we're not looking at any change in direction. This ball is just traveling downward under the influence of gravity, which you've already learnt earlier in your school careers, 9,8 meters per second squared. But we're going to work with 10 meters per second squared here. It asks you to find the time required for the ball to hit the ground using equations of motion, and then the velocity with which it hits the ground. That would be the final velocity after it has traveled from the balcony to just before the ground stops it. So the final velocity is not zero. We're talking about the maximum velocity the ball reaches under the influence of gravity before the ground actually stops it. And then I would like to challenge you to draw the sketch graphs for the velocity versus time, change in position versus time, and the acceleration versus time. So this has been a long, detailed, rigorous video, but an exceptionally important video, helping you to step into more complex kinematic problems involving graphs and equations of motion. I'm going to now end off, and in the next video we will look at the solutions of these two problems, and then we're going to delve deeper into graphs of motion and look at more complex problems where we can employ the equations of motion in order to help us solve them.